session. I'm Jalal Gilan from University of Paris 7, and I will share this session. So the next talk is an invited lecture, will be given by Professor Richard Crooks from University of Austin at Texas. He will talk about Kochel Linderman encapsulated nanoparticle, theory, synthesis, characterization, and electrocatalysis. Please, Professor.
Okay. Can everyone hear me okay? Too loud? Not loud enough? It's okay. 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 Well, first of all, I want to thank the organizers for the invitation, and I'd like everyone to know that I'm available to come to Paris anytime and give a lecture, because this is my favorite. This and Austin are my two favorite places on the planet. So thank you very much. And I have a tough audience of electrochemists here, so I have to really watch myself. I think people, if you have questions as I go along, I think you can feel free to interrupt, and we'll just see how far we get here. Let me thank my co-workers. Almost all the work that I'll tell you about today was done by a very good graduate student in my group, Emily Carino. And Graham Henkelman is a theorist, and you'll see towards the end of the talk his contribution and also the contribution of his postdoc, Hyun Yu. And Dave Yancey is also in my group and made some contributions to this talk as well. Okay, so first I have to show you a little bit about my other favorite place, which is Austin. This is the University of Texas. It's the largest university in the United States. It's about 52,000 students, something like that. This is Austin, the downtown area. Looking south, here's the downtown. It's also the capital of Texas. This is the state capitol building. It's a 1.01 scale replica of the national capitol in Washington, D.C., just a little bigger. Okay. And then the University of Texas is right behind the Capitol building. And we have a very good electrochemistry group at Texas. You'll recognize some of these people. I'm sure everyone recognizes my colleague Al Bard. Anybody recognize this guy? Adam Heller? Okay. So everybody in this room has on their possession, I'm sure, one of Adam's contributions, which is the lithium anode in the whatever computer or cell phone battery you happen to have with you today was invented by Adam. By John Goodenough. This is John Goodenough. Any of you who happen to be diabetic probably have one of Adam's glucose sensors, with you or at home. This is one of my junior colleagues, Keith Stevenson, who does battery-related things, among other things, also an electrochemist. And then some of you might recognize this guy. Anybody recognize this guy? Larry Faulkner. So Larry, of course, is Bard's co-author in Electrochemical Methods, the book Electrochemical Methods. And then subsequently, he started as a graduate student with Al Bard in 1966 and did some of the very first ECL work with Bard, and then eventually became Bard's boss as president of the university. Actually, I was chairman of the Department of Chemistry, so I was Bard's boss for a while, too. He never listened to either of us about anything, I promise. But Larry subsequently retired as president of the university and went off and ran a private foundation, but he'll be back in a technical capacity starting next year. So we'll have Larry back doing electrochemistry. So it's a real good electrochemistry group. And if you happen to be anywhere near Austin, I encourage you to stop by and visit us. Okay, so I sort of agree with George Whiteside's. I don't think you need to have a product in mind, when you do science. But I do think it's good to have an objective and to build a fence around that objective. And so we do have an objective for the study I'll tell you about today, which is to develop an experimental model catalyst for the oxygen reduction reaction that can be compared directly to theory. This is not a talk about replacing platinum, okay? And so nothing, that you're going to see here today involves replacing platinum. It more involves trying to understand platinum and electrocatalysis in general, and then doing a few experiments to test that understanding. And so this is really about very fundamental modeling type studies. So, because if you think that this is about replacing platinum as a catalyst, you're going to be deeply disappointed, okay? So please keep that in mind. So if you want to compare first principles theory to metallic electrocatalysts, there are some requirements, my colleague Graham Henkelman tells me. So the first one is a very high degree of monodispersity in size, composition, and structure. So normally we're looking at billions and billions and billions of catalytic particles, and if you want to correlate their function to theory, then they all have to be about the same, structure, size, composition. Or you can develop ways of looking at one catalyst at a time, but that's a little harder. There are people working on that. There are even a few published papers, but it's a much more difficult problem. The catalytic particles need to have less than 200 atoms and really maybe 150 atoms or less, because DFT calculations just they get too computationally expensive when they get to be any bigger than this. This is really the absolute upper limit for first principles calculations. And then, Henkelman would like to know the identification of the atomic coordinates of all the atoms in all the catalytic particles. Well, that's not going to happen anytime soon in my lab. But, we try pretty hard to approach that ideal. Okay, so this is the problem or the objective, and this is the fence. These are the rules that we have to follow to address that objective. So here's an outline. There's just 3 parts. I need to give you a little bit of background and tell you about the synthesis and characterization of these materials we call dendrimer-encapsulated nanoparticles. And then I'm going to show you some published work just to get you calibrated on what we're trying to do. Show you some electrocatalytic properties of some monometallic, actually platinum, dendrimer-encapsulated nanoparticles. And then I'll move on to some new work that we're real excited about that's not even written up into draft form yet, but will be soon, I think. Okay, so the first thing I need to tell you about, if you don't know already, is dendrimers. There's actually quite a bit of work in France as one of the real hotbeds of dendrimer activity. So you probably already know about these. But dendrimers are quite monodispersed polymers. They're not perfectly monodispersed, but they're as good as any polymer there is. They're prepared starting with an ethylene diamine core and then 2 reactions, a Michael addition reaction followed by an amidation reaction. And what happens during these 2 reactions is effectively the 2 primary amine groups here are multiplied by 2. And now you can go through this cycle again, and in the next iteration of 2 reactions, you go from 4 to 8 amines, and you can keep doing this up to about 10 cycles. And then finally, there's so much steric crowding on the periphery of the dendrimer that you can't keep doubling the number of terminal groups on the dendrimer. Now, by the time you've done these reactions about 4 times, there's enough steric crowding that the polymer no longer is planar, but it starts to adopt a globular shape as these end groups here try to get out of each other's way. And so this is a planar projection of what's really a 3-dimensional object. It's about, as it says here, this is the generation 4 polyimidoamine dendrimer. And it's about 4.5 nanometers across, so it's about the size of your average enzyme. Because of the way it's prepared, but these iterative reactions, it has a hole in the middle that, of course, is just waiting for somebody to put something inside of it. And it has passageways into the interior of the dendrimer, which is just waiting for a small molecule to come in there. and find that object in the interior of the dendrimer. And then it has lots and lots of peripheral groups here. And for this dendrimer, there's 64 of those. They can be used to link the dendrimer onto a surface. You can solubilize the dendrimer in just about anything. We've done catalysis reactions in supercritical fluids, organic solvents, Fluoris solvents, water. I guess that's it. And then the most important thing, though, is that these branch points are all tertiary amines. Here you go, or you can see them right here. And those primary amines have lone pairs of electrons, and those lone pairs of electrons like to coordinate or react with transition metals, like copper, platinum, salts, palladium complexes, things like that. Okay? So because the dendrimer is more or less monodisperse, that means it has a more or less monodisperse number of these interior tertiary amines. So this generation 4 dendrimer has 62 interior tertiary amines. So if I take a metal ion, and we've done this with all these metal ions shown here, and mix it with the dendrimer, those metal ions will partition into the interior of the dendrimer and coordinate or react with those tertiary amine sites in fixed stoichiometries. So if it's an ideal dendrimer, 62 of these metal ions will partition into the interior and be very strongly bound to the tertiary amine sites. Now if I add a reducing agent like borohydride, those 62 ions will be converted into 62 atoms. That's an energetically very unstable situation. Those atoms would like to, nucleate and grow, and they do very quickly, faster than we can measure, into a single particle. And that particle now is trapped inside the dendrimer, but primarily sterically. We've using EXAFs and other techniques, and electrochemical techniques particularly, the surface of this particle, this metallic particle, is clean, okay, within our ability to measure it. That means that the dendrimer itself, these functional groups inside the dendrimer, are not poisoning the surface of the particle. So this is like a ship in a bottle type of synthesis. You put the little parts in, and then you make a big part, and that now it's sterically confined in there. But the surface isn't poisoned. So they're pretty monodispersed particles because it's a template synthesis, and the surface of the particle is accessible for catalytic reactions. And so not only is it possible to make monometallics, but we've made alloy particles of various sorts, core shell particles, and we even have one paper on cadmium sulfide. So you can make semiconductors as well. Okay, this is just a cartoon, okay? And it's just to show you that the dendrimers are not, as regular as that two-dimensional projection showed. But it's also to show you this is a 147 atom gold particle inside a bigger dendrimer, generation 6 dendrimer. This dendrimer is terminated with hydroxyl groups, and I think everything I'll talk about today, the peripheral groups are hydroxyl groups. That's important. It's better to be hydroxyl groups than primary amines because primary amines coordinate metal ions too. And we want the metal ions only in the interior of the dendrimer, not on the exterior. If they're on the exterior, if they coordinate to the exterior, they'll basically polymerize the dendrimers, and they'll just precipitate. So it's important that the peripheral groups be non-coordinating. But this is just to show you that there's easy access, almost unhindered access, we think, of small molecules to the surface of this particle through pretty big pores inside the dendrimer. Okay, so here's the basic. And, if you're thinking to yourself, how does that guy know these particles are really inside the dendrimers? We've published a lot of papers, and other people have too now. And so I think it's generally accepted that cartoon I just showed you is okay. So I'm not going to talk about the detailed structural characterization and how we know that. So here's the basic electrochemistry experiment we do. This is the basis of what I'm going to talk about today. So this is a 4th generation dendrimer now, hydroxyl terminated, and we've already added platinum tetrachloride. Platinum tetrachloride undergoes a ligand substitution reaction. Chloride falls off. A water molecule or two comes on. Once that's happened, there's a covalent reaction between the primary amines and the platinum. And it's possible in this dendrimer to have a one-to-one stoichiometry between the platinum complex and the tertiary amines. So I can put a maximum of 62 platinum ions inside this generation 4 dendrimer. Okay, so I've done that. Now I've added borohydride. The particle has formed under the influence of the reducing agent. And now I'm going to graph that onto a glassy carbon electrode. Now, a powerful aspect of this technique is that this particle, before I graft it onto the surface, I can take this and characterize it. I can, by your whatever favorite technique you have, dynamic light scattering, TEM, XAFs. These particles are small, 40 to 200 atoms, so they're too small to do normal X-ray diffraction. But we do a technique at the synchrotron called X-ray diffraction pair distribution function. And so with a synchrotron, we can actually do X-ray diffraction on these. Not so easy as just doing powdered diffraction in your own chemistry department, but possible. Okay, so we take the dendrimer encapsulated nanoparticle inside its dendrimer host, glassy carbon electrode, and just do some scans in whatever electrolyte, it doesn't really matter, in water, and do a few scans. And what you see when you do this, on the very first scan, there's a little extra current here. And something is happening, and we really don't know whether this current is due to something happening, to these hydroxyl groups on the periphery, or if it has something to do with oxidation of the carbon, or what. But this step, this first scan here, irreversibly attaches the dendrimer onto the electrode surface. If we don't do this, the dendrimers will fizzy-sorb, but they're not so stable. They tend to fall off. So we really don't know what's happening. We really don't care what's happening here. Something is happening to nail these dendrimers to the surface. This process doesn't affect the cargo. It doesn't affect the nanoparticle, because we can also analyze, after we've done this attachment, we can analyze the particle again. We can look at the coordination number by XAFs, and it's unchanged. Okay, and then you can do a couple more scans here, and there's no further change. So this cyclic voltammogram is just to show you that something is happening here that attaches the dendrimer to the surface. Okay, so here's the first electrocatalytic experiment we did with these materials. This experiment was done by Hee-Chung Yi in my group. He was a postdoc and actually, or a graduate student, and then postdoc for Bard. I saw he was on a paper earlier this morning as well from the Bard group. So here's the experiment. We attach the dendrimer encapsulated nanoparticle to a glassy carbon electrode and put it in a sulfuric acid solution that's saturated with oxygen in water, and then scan the potential. And what we're hoping is that we'll see oxygen reduction on this nanoparticle. So there's two things that have to happen for that to occur. One is electrons have to move from the electrode up to the nanoparticle. Now, these nanoparticles, I'm showing you this nanoparticle in the center of the dendrimer. Actually, we know that it's an ensemble average, and actually they're not in the center. They're distributed in, symmetrically in this region of the dendrimer. So they're, on average, a little bit off-center, but near the center. But some, I'm sure, are over here on the side. Some are right in the center. Distribution of sites. So the electron has to be able to tunnel from the electrode up to the nanoparticle, and oxygen needs to permeate through the dendrimer, encounter a clean spot on the surface of the nanoparticle, and then whatever product, peroxide or water is made, has to be able to leave. So here's the three first experiments that Hee-Chung did. The first one is just naked glassy carbon electrode, scans the potential out negative. Here's oxygen reduction on glassy carbon. Next experiment, same as the first, except he'll just put a dendrimer on the surface with no nanoparticle, and the response is the same. Now he puts a 40-atom platinum particle inside the dendrimer, just as exactly as is shown here. It does the same experiment, and there's a shift of about 600 millivolts towards more positive potentials, indicating that the platinum nanoparticle is electrocatalytically active. Okay, so this was a real important experiment for us because it showed that this basic concept was going to work, and that this is an accurate, if somewhat simplified, picture. So we've done quite a bit of quantitation using this approach, and I'm not going to go into the details because I really want to talk about something else today. But I do want to show you just a little bit. So these are monometallic platinum dendrimer encapsulated nanoparticles. The dendrimer in this case is 6th generation hydroxyl terminated dendrimer, and we can make dendrimer encapsulated nanoparticles of arbitrary size inside the dendrimer. And so, again, this is He-Chung's work. What he did was he made particles consisting of 55, 100, 147, 200, and 240 atoms. So you have very precise control over the number of atoms in these particles. And then he did, quantitative rotating disk voltammetry and compared it to a bulk platinum electrode. So the black curve here is rotating disk voltammetry for bulk, just a bulk, rotating disk electrode of platinum. And then the red line here is the biggest nanoparticle, okay, the 240 atom particle. That's about as big as we can make in this dendrimer. You can see there's a shift to more negative potentials here, indicating that this nanoparticle is not as good a catalyst as bulk platinum. And then as he gets smaller and smaller, you could see further and further shift, and this is published data and has been quantitatively interpreted. And so it gets worse and worse as the particles get smaller. And then finally, something really interesting here happens when we get down to 100 atoms. There's actually a shift in the mass transfer limited current. And we're not sure what this is due to yet. We're actually actively studying this. It's one of two things, though, I think. It's either a shift in the product from water to peroxide that's driven by the size of the particle, which would really be amazing. This is only a 47 atom difference in average particle size, and yet it looks like we're now making peroxide rather than water. And if you're a water oxygen reduction person, you can imagine that there's just not enough space on these really little particles for dioxygen to have its dioxygen double bond parallel to the surface, and then it might bind end on and make peroxide instead of water. You can imagine all kinds of things. So that's one possibility. The other possibility is it's a mass transfer effect. And so we're studying this problem, so we don't know. It's one of those two things, I'm almost sure. And as you get even smaller, you can see the mass transfer limited current goes down a little more, and we continue shifting the potential more negative, indicating the catalyst is getting worse and worse. This is a plot down here of the specific activity where we've taken into account the total number of surface platinum atoms in these particles and then plotted it as a function of the size of the particles. And you can see these are really not very active materials until they start getting bigger, and they never are as good as bulk platinum. That's fine. We're not trying to make a better catalyst here or use platinum more effectively or anything like that. We're just trying to make really monodispersed materials with a very small number of atoms that we can compare to theory. Okay, so let me tell you a little bit about our view of, or at least Henkelman's and my view of how oxygen reduction works. So let's take here's dioxygen, and here's the catalytic surface that we're interested in. And let's take the case, let's divide up metals into two categories, noble metals and reactive metals. So let's think about reactive metals first. So reactive metals are things like iron, nickel, molybdenum, things that form oxides spontaneously. So in that case, it's very easy, if you follow the red line here on this sort of Arrhenius type diagram, it's very easy to break the dioxygen bond because that happens naturally on reactive metals. Okay, so that happens easily, but now you fall into this energy well here, and that metal oxide is extremely stable, and the oxygen never leaves the surface. That's bad, okay? The alternative is metals like silver and gold, which don't form oxides very easily. Now we have a big energy barrier to break the dioxygen bond, but if that happens, it's easy to get, the product, the hydroxide or whatever is formed on whatever oxygenated species are formed on the electrode or on the nanoparticle in our case, off. Okay? So now, if you look at this plot from a very famous Norskopf paper, actually I saw Whitesides had this same plot in his talk. It's divided into reactive metals and noble metals. Okay, here's just a couple noble metals over here, just silver and gold, lots of reactive metals. And up at the top of this, people call these volcano plots. Up at the top of the volcano, or near the top of the volcano, is platinum. And the reason platinum is good is because it is the best combination. I should change that. The reason platinum is okay. It's everyone says it's the best. The best is not necessarily good. Okay? And platinum is actually not an especially good catalyst for oxygen reduction. It's got kinetically slow, it's easily poisoned by carbon monoxide, all the things we've heard about here for the last few days. But it's the best of these, monometallic catalysts. So it's up near the top of this volcano, and it's because it has the best combination of being reactive, so it can break the dioxygen bond, but being sufficiently noble that it can release the products. That's why it's up at the top. So what Norskopf suggested was building these things he calls near-surface alloys. So now what we're going to do is we're going to take another metal like palladium and a second metal like copper, which is an electron donor, and build an infinite two-dimensional surface. So the bottom layer is going to now donate electrons up into the d orbital of the palladium. It's the d orbitals that matter for oxygen reduction. It's these oriented orbitals with localized electrons that are going to have to get up into that oxygen in order to break the dioxygen bond. The free electrons don't matter. It's the d electrons. And so this is going to make, by putting this donor down here, it's going to make palladium look more like platinum. In fact, maybe even push it up here a little closer to the very top. Now, I have to warn you again, I'm not trying to make a better catalyst, because if I were, I sure wouldn't be studying palladium, okay? I'd be, down here further, looking at these earth-abundant metals, okay? But this is the idea that we start with in our studies then, okay? Now we're going to move from monometallics to core shell metals. Okay, now let me just look at my time here. Okay, 20 minutes? 20 minutes, okay, no problem. Okay, so we're going to make these core shell particles by underpotential deposition. I think everybody knows what underpotential deposition here is, but if you don't, let me remind you. I have a first metal, so this could be platinum, just a bulk polycrystalline platinum electrode. And now what I'm going to do is immerse it in a solution of copper 2+ and start scanning the potential negative. And what I see, these are experimental data here, what I see is, there's a peak here, and that peak is well positive of the thermodynamic potential for reduction of copper. And what's happening is that the work functions of copper and platinum are such that copper prefers to deposit on platinum more than copper prefers to deposit on copper. And so just a single monolayer of copper will deposit on this platinum surface, and then after there's a monolayer, now I'll start to see bulk deposition of copper, and I'll see, grow multi-layers real quickly. Okay? So for what we're going to do, we're always going to be to the left of this line. We'll always be doing under potential deposition. Okay, so here are some of our first experiments. This is, in fact, copper under potential deposition on platinum dens of 3 different sizes. So this is the reason we use these numbers of atoms, 55, 147, is that these are magic numbers for closed shell cubo-octahedral particles. Okay, and so here's the first one. This is the black is always the background scan, which is a scan of just the platinum den in an electrolyte solution, but with no copper added. So it's just the background. Okay. Now you add a little bit of 10 millimolar copper and do a scan. That's the red here, and you can see here's the deposition of a monolayer, we think, of copper on this little particle here, and then this is the stripping of the copper from the particle. Now we go to a little bit bigger one, a little bit bigger den. So this has 3 closed shells. You can see now here's the deposition, stripping. You can see there's a little more charge, which there's, you would intuit that there should be. There's this, when we immobilize the dendrimers on the electrode, even though the particles have different sizes, the same number of dendrimers immobilized, because the dendrimer is what's taking up the space on the electrode. So there's always the same number of those. So the number of particles is the same, just their size is changing, roughly the same. Okay, and then this one, we can't go to the next closed shell here, which would be 309 atoms. We just can't make particles that big inside this dendrimer. And so instead what we look at is a 225 atom particle, which is a magic number for a truncated cubo-octahedron. So it's a slightly different structure. And now, here again, you see, quite a bit more charge consistent with the higher surface area on that platinum particle. When you just look at these cyclic voltammograms, there's 2 things that you notice. One is the charge is getting bigger. Okay, that's good. That's consistent with what we would expect. The other thing is you can just start seeing a little more peak definition as you go from small to large. And it's very tempting to say, well, these peaks are due to deposition on different facets. You can see this is a 100 facet here, and then these are 111 facets here. And so it's very tempting to say, first we deposit on one facet, and then we deposit on another facet. And this is well known from the bulk platinum copper UPD literature. And, why not here? Well, it's because there's not much of a facet on these small ones. The facets are just a few atoms, and so it's not really a facet. It has a lot of character of edge atoms and corner atoms. Okay, so this is what, we believed when we saw these voltammograms. That's the way we interpreted them, very qualitatively. Now, what we want to know is how much copper is there on each of these particles, at least relative to the number of surface platinum atoms. And the way we get at that is by doing hydrogen adsorption, desorption, or I actually heard someone call this hydrogen UPD. That's fine too. It is also hydrogen UPD. So we immobilize platinum dens, 225 atom platinum dens on an electrode surface, and then scan out here into the hydrogen region. You can see all the normal things you see for platinum. Here's platinum oxide reduction, and now we see some hydrogen here, adsorption and desorption of hydrogen atoms. From this current here, this charge here, the desorption charge, we can measure the total charge, due to desorption of hydrogen atoms. And that turns out, in this case, to be 222 microcoulombs. Now what we're going to do is we're going to do the same experiment on the same electrode, but with some copper, with 10 millimolar copper in solution, do deposition and stripping, and measure the charge due to the stripping of copper. And we're going to compare it to this number, and then that should give us an accurate ratio of the number of copper atoms to the number of surface platinum atoms on the particles. And that's what this is. So here we are. this is, back to copper UPD on this 225 atom truncated cubooctahedron. So what we're looking at here is this charge now due to copper stripping, and we compare that. This is the charge due to copper stripping. Of course, there's 2 electrons for copper, just 1 for hydrogen. And so we use this simple formula and define this parameter theta copper. Theta copper is the ratio of the number of copper atoms to the number of platinum surface atoms, not total number of atoms, surface atoms. And lo and behold, this turns out to be 1.0. And when we first got this, we thought, oh, perfect, just like bulk, exactly. This made us very happy. Until Dave Yancey, pointed out in our subgroup meeting where we were talking about this, it shouldn't be 1.0. It should be a lot bigger because these are not bulk surfaces. These are nanoparticles. And if this were analogous to bulk copper UPD, then we should deposit yet another shell around this, a close-packed shell around this platinum shell, or the outer platinum shell. Okay, well, platinum-225 has 140 surface platinum atoms. So if it were a closed copper shell, in other words, if we just went to the next magic number up, the next closed shell, there'd be 230 copper atoms. And so the expectation for the nanoparticle is that theta copper should equal 1.6. So we're much smaller than that. So this is not bulk. This is different than bulk. Why? It's just there's more space. The nanoparticles are radially distributed. And so every time I move out, I have more space than I did on the inner shell. On bulk, you're confined. Okay, your neighbors are confined onto 2 dimensions. Here, 3 dimensions. And so the question was, why is this? This is a case, by the way, where you get this result that you're expecting, and you're very excited. Of course, it's the boring result. So why do you get so excited, right? And now you get something that you don't expect, and now that's actually much, much more exciting because now you have to figure it out. And so the first thing we thought was, are there unique sites on these nanoparticles, where copper deposits? And the likely sites are the facets. And so we developed a model that we thought might account for this observation. So let me just recap the observation. So the hydrogen adsorption data tell us that the core really is a 225 atom platinum particle. There are these 2 separate copper UPD sites, at least on this big 225 atom particle. And so we could imagine that some of that charge, some of that copper is being deposited on the 111 surface, some on the 100 surface. And we might imagine that copper might not deposit on the edges because those are very high energy sites, and it might not be the place where copper wants to be. And so this is the model we developed with our colleague Graham Henkelman. This is the same truncated truncated octahedron that we were just looking at. It has, of course, 140 platinum surface atoms. That's the normal number of surface atoms in this particle in that outer shell. And now what we'll do is we'll just decorate just the facets with copper atoms. We'll close pack, but only on the facets, and we'll leave the edges exposed. And that turns out to take 150 copper atoms rather than 230 on the previous slide. And so now, with this model, theta copper is equal to 1.1. So we think we have a good model. Now we need to test the model. So we do that by in situ electrochemical EXAFs and other techniques, but this is the most powerful in this case. This is the cell we use. We do our experiments at the Brookhaven synchrotron in New York, upstate New York. And this is the cell. The main things are in the cell is that the DENs are immobilized on a carbon paper electrode. The problem with this experiment, this is a real hard experiment, and the reason is there's not many atoms, not many platinum atoms, and not many copper atoms. So this is actually a very difficult experiment to do. This is the cell then. This cell is now, mounted in a holder. This is the beam coming through here. When one does transmission X-ray absorption spectroscopy. This is the detector. We'll actually mainly be doing fluorescence due to the weak signal. And so here, right here, they'll be bolted on a fluorescence detector. XAS, we don't need to really talk about how XAS works, I don't think. It's sort of mysterious, but it's actually very similar to UV vis spectroscopy. It's just X-rays being absorbed instead of visible photons. It's a little more than that, but not too much. Okay, I'll show you a picture, so here's the people. This is Emily. This is the person who did most of the work I'll be talking about, and these are other people in my research group. Here they are at the beam line. For those of you who have done this, they're out of the picture. There are some cots where they sleep and things like that when we get our beam time. Okay. Okay, so here's the approach we use for doing the XAFS experiments. So as I said, the DENS are immobilized on a copper paper electrode. Copper is deposited underpotentially by stepping to this potential we call E full. E full is the potential at which we have a full monolayer, a full copper UPD monolayer. If we went any further out here, we'd start depositing bulk copper. So we step from this potential to this potential, wait for the current to die away, and now we're ready to collect XAFS data. It takes about 2 hours to collect enough data, to get the signal to noise to a reasonable level. So here's what the data look like. This is the black here are the data collected from the platinum edge, and then the black data down here are from the copper edge. And what one does to analyze XAFS data is simulate using software, the software called Ififit, which everyone has agreed, almost everybody uses Ififit, I think. So everyone's agreed. If we're lying, we're all telling the same lie, okay? But this is what everybody does. And we fit it, and you fit it as best you can. These particles are so small and there's so little signal that we can only, for those of you who are XAFS experts, we only fit out to one coordination shell. This is just all noise out here. We don't attempt to fit out there. If you have more metal atoms or better metal atoms, you can fit 2-3 coordination shells. We only fit one coordination shell. The main thing that's useful that can be extracted from XAFS for the types of experiments we do is the coordination number. The coordination number tells you how many, for example, for the platinum edge here, if we look down at this table for the platinum-platinum coordination number, the coordination number is, on average, how many platinum atoms are next to every other platinum atom. Okay? So if you imagine, these blue sphere here, this is platinum. This is on an edge. So it really only has 2 or 3 nearest neighbors in its first coordination shell. So its coordination number might be 3. But buried down in the middle of this particle is another platinum atom, and it has 12 nearest neighbors. So what I'm going to do is I'm just going to sum up, all of the, for every platinum atom, I'm going to say, how many nearest neighbors does this one have? And the range is 3 to 12. And I'm going to take the average, weighted by where all of the atoms are in the particle. And it turns out the calculated coordination number for this model is 9.5, and we measure 9.7. Okay? XAFS on particles like this is considered, this may look like a big number to you, but to XAFS people for materials like this, it's actually a very small uncertainty. So we feel very good about that. And we can look at platinum copper. Now we're asking for these surface platinum atoms, well, actually, all the platinum atoms, what's the average number of copper nearest neighbors? And in our model, it's 2, because you remember, those platinum atoms that are buried in the interior of the particle have 0 copper nearest neighbors, and we're doing a weighted average. And what we measure is 1.3, and then this is copper-copper. We measure 3.5. The model says 4.2, and then for copper-platinum, we measure 3.4. The model is 3.2. This is very powerful confirmation of the structure that, our structural model. We can create other types of models and calculate the coordination numbers for those models and go back and compare to the experimental results, and they're not good matches. This is the only one that's really a good match, and it's also completely consistent with the electrochemical data. So we think this is a pretty good representation of reality. Okay, now I need to look one more time just to make sure I'm not going to... Ooh, I'm getting pretty close here. How much more time? 5 minutes, okay. All right, we'll go through the DFT really quickly, which I think will probably be a relief to almost everybody. Okay, so let's switch gears a little bit. Let's talk about 147 atom particles. They're smaller, they're much easier, although still very time-consuming to do first principles calculations on. So we're shifting now not to a truncated octahedron, but a cubooctahedron, 147. So there's 100 texture, and then there's also facets here that are 111. Okay, and what we think is, because we see these two deposition peaks, is we think it's possible that there's first deposition on this facet, on the square facet, and then on the triangular facet second. And we want to see if we can understand that or correlate it to theory, which is the whole point of this. These are just, okay, so this is a slide. Here's the copper under potential deposition again onto the platinum 147 atom platinum particles. Okay, and what we're going to do is we're going to just deposit a little bit of copper, stop here, okay, change the solution, just leave that copper, a little bit of copper on that platinum den, and now do hydrogen deposition and stripping, okay? And that's what this is. Now we're going to do another one. We'll stop here. It's all done on the same electrode with the same nanoparticles, the whole experiment. And so what you see when theta copper is 1, okay, that's where we're pulling the electrode out here, okay? We don't see any hydrogen adsorption or desorption. Why? Because the platinum sites are covered by copper, okay? Up here, where we have smaller fractions of copper coverage, we see first one peak, and then at higher coverage, or at even lower coverages, a second peak start to emerge. And so what we say is, well, this is deposition first on the 100 facet, and then copper deposition on the 111 facet. That's the model. Okay, so here's the DFT calculations. So here's our particle. We're going to first put one atom on this square facet here, and the energy calculated for that is minus 3.71 eV. Now, it turns out to put all the other atoms on here takes this energy, has an energy of adsorption either approximately the same as this value. So as soon as we get one atom on here, all of the others go on immediately at that same potential. Okay, now we start with this structure and we put one atom on the surface, on the triangular, on the 111 surface. The energy for adsorption of that is minus 3.07 eV. So it's a little bit, that energy is weaker, okay? And so that's a little harder to do, but once that first one's on there, all of the others are easier, more negative energies. So as soon as I put this first atom on here, it makes it easier for the second, third, fourth, fifth atom to go on to that facet. Okay, that's what the calculation says. And so we can just, now we're interested, we're correlating these peaks, these two peaks in the cyclic voltammogram to these two energies. And we calculate, just subtract these two energies. That's 0.64 EVs. You have to divide by 2 because there's 2 electrons to get volts. 0.32 volts. So this is the voltammogram that we're correlating to. And we're looking at these two peaks right here. We call this delta E deposition. Well, what we measure is 0.7. DFT says 0.32. Not very good agreement. So we go back to our theory collaborators and we say, what are you guys doing over there anyway? Well, we're working in vacuum, And I said, no, not vacuum. Something better, please. So what they do is they take sulfate and they cover this whole particle with sulfate now, which is a much more reasonable representation than a naked platinum particle in vacuum of what we're actually doing. And now they go through the calculations again. And this time, it takes some energy to pull one of those sulfates off, but once the sulfate's on, it's actually a little bit harder now to put on that first copper atom. On the naked surface, minus 3.71. The more negative this number, the easier it is for that copper atom to stick, I should say. Okay, so the more positive the number gets, the harder. Okay, and then, you know, you can pull off another sulfate and, you know, keep putting these on. And you can see that what's happening here is as soon as you put one copper atom on, it's really easy to put the rest on. Okay, this is a little bit, you know, if you remember back to your Barden-Faulkner days, you know, this is like an ECE reaction where the second step is easier than the first step. And so this is a peak generating step. Okay? Okay. Anyway, we can go through the whole process. This is the whole set of DFT calculations, and I won't bore you with the details. I'll just tell you that now, when you do this same calculation, taking into account the sulfate groups that are on the surface, the experimental number, you remember, for the difference in those deposition peaks was 70 millivolts. We now get 45 millivolts. So we're actually getting a little bit closer. And finally, we made one more adjustment. And this was a very good idea by our theorist friends. What they did was they went into the literature of bulk copper UPD, and they did a DFT calculation for bulk deposition of copper, and then compared that to the experimental number. They were close, but not exactly the same. And so they generated a correction factor from the DFT number to the experimental number, just a few tens of millivolts, and said, okay, let's apply that correction to these nanoparticles, the same correction, okay? Because, you know, our DFT is off a little bit. Let's correct the nanoparticle number for the amount that we know it's off on the bulk. And so that's what they did. It wasn't a big correction. It's a pretty small correction. But now you can see we're getting really, really close here, 0.7, 0.97. So we're really getting good agreement between the DFT results and the deposition results for you know, experimentally measured deposition results. Of course, what I tell them, next time, you guys tell us what the number is, and then we'll do the experiments, okay? They looked really shocked by that idea. Okay, let me finish up. I'm sorry, I know I've gone over a little bit here, but let me finish up. So the one point I want to make is that these monometallic DENs have size-dependent electrocatalytic properties, and really just changes of 20 or 30 atoms in a particle are easily big enough to see if you remember the rotating disk voltammetry results. No problem. And then you can prepare these core shell DENs by underpotential deposition, and you know, we're beginning to understand some of their properties from, you know, these DFT calculations. And what we're going to do now, or what we're working on now, is to correlate the effect of size and full and partial decoration. You remember back to the Norskopf idea with the near-surface alloys, one metal on top of another. So now what we're going to do is go back and look at oxygen reduction, where we have, for example, a copper core and a palladium shell. There's a few little tricks you need to play to do that by using underpotential deposition, but it's possible to do. And compare DFT calculations for oxygen reduction to experimentally measured values, and then start looking at these partially decorated nanoparticles, where we just decorate one facet. And now we ask, what happens with oxygen reduction, you know, when there's just one type of facet covered by the second metal? So anyway, I'll let off there, and I'll thank you for your patience. I know I went on and just show you my research group at Texas, and thank you for your attention.
And now we have time for one or two questions.